Welcome to another episode of Tech Talk, where we explore the fascinating world of technology and the systems that shape our digital experiences. Today, we're diving into a topic that often flies under the radar: the reliability of clocks in distributed systems. You might think time is a straightforward concept, but in the realm of technology, it gets surprisingly complex. So let's put on our headphones and jump right in. To start, let's talk about the limitations of traditional time synchronization methods, particularly the Network Time Protocol, or NTP. While NTP is a common tool for syncing clocks across devices, its accuracy has inherent limitations. This is largely due to factors like network round-trip times and errors from quartz drift. Think about trying to measure the time it takes for a message to travel across the internet. It's not just about the clock on your device, but the performance of the entire network. In distributed systems, effectively ordering events requires a clock that surpasses the inaccuracies introduced by network delays. This is where logical clocks come into play. Unlike physical clocks that track actual time, logical clocks focus on the order of events. They work by incrementing counters, avoiding the pitfalls of relying on quartz crystals, which makes them a more reliable option for event ordering. Even if you can read a machine's clock with microsecond or nanosecond precision, that doesn't guarantee accuracy. Quartz clocks can drift, leading to errors of several milliseconds. When syncing with an NTP server, especially one on the public internet, you might only achieve accuracy within tens of milliseconds. During peak network congestion, that error can balloon to over 100 milliseconds. So what does this mean for our understanding of time and technology? Instead of viewing a clock reading as an exact moment, we should think of it as a range of possible times, defined by a confidence interval. For example, a system might be 95% confident that the current time is between 10.3 and 10.5 seconds past the minute. If there's an uncertainty of plus minus 100 milliseconds, those microsecond digits in the timestamp lose their significance. Calculating this uncertainty is essential. When using a GPS receiver or an atomic clock, manufacturers typically provide an expected error range. However, if you're syncing with a server, the uncertainty depends on factors like drift since the last sync, the server's accuracy, and network round-trip time. Unfortunately, many systems don't expose this uncertainty. For instance, when you call clock get time, you get a timestamp, but no indication of its accuracy. You could be looking at an error margin of 5 milliseconds or even 5 years. A notable exception to this is Google's TrueTime API, which is utilized in their Spanner database. When you request the current time, it returns a pair of values, the earliest and latest possible timestamps. This provides a clear view of the confidence interval, which is especially beneficial in distributed systems. Speaking of distributed systems, let's discuss snapshot isolation in databases. This feature allows read-only transactions to see a consistent state of the database at a specific point in time without interfering with ongoing read-write transactions. It operates by assigning an increasing transaction ID to each operation, ensuring that if a write happens after a snapshot is taken, it won't be visible to that snapshot transaction. However, when databases are spread across multiple machines or data centers, generating a globally unique transaction ID can be tricky. The transaction ID needs to reflect causality. If one transaction reads a value written by another, it must have a higher ID. This is where things can get complicated. Some distributed systems use sequence number generators, like Twitter's Snowflake, to create unique IDs. Yet these often can't guarantee causality because the time taken to assign blocks of IDs may exceed the speed of transactions occurring in the database. So, can we use timestamps from synchronized clocks as transaction IDs? Theoretically, Yes, but the uncertainty surrounding clock accuracy presents significant risks. Spanner cleverly implements snapshot isolation across data centers using the TrueTime API. It leverages the confidence interval to determine the order of transactions. If two confidence intervals don't overlap, we can be certain of their order. However, if they do overlap, we can't determine which transaction occurred first. To maintain consistency, Spanner waits for the length of the confidence interval before committing a read-write transaction. This ensures that any transaction reading the data is sufficiently later in time, preventing overlaps. To keep wait times low, Spanner minimizes clock uncertainty by deploying GPS receivers or atomic clocks in each data center, achieving synchronization within about 7 milliseconds. While these concepts are groundbreaking, they haven't yet seen widespread adoption outside of Google. Now, let's consider another example of how unreliable clocks can cause issues in distributed systems. Imagine a database with a single leader for each partition. Only this leader can accept writes. How does a node ensure it remains the leader and can safely accept writes? A common method is to use a lease with a timeout. The leader must periodically renew this lease to maintain its status. However, this approach has its drawbacks. If the expiry time on the lease is set by a different machine and compared to the local system clock, significant clock drift can lead to problems. The code might believe it's still the leader, when in reality, it has lost that status. Additionally, the code assumes that the time between checking the lease and processing a request is negligible. But what if there's an unexpected delay in execution? If the thread pauses for an extended period, the lease could expire and another node might take over as leader. By the time the original node processes the request, it could mistakenly believe it's still in charge, leading to unsafe operations. Is it unreasonable to expect a thread to pause unexpectedly? Unfortunately, it's not. In distributed systems, the reliability of clocks and time management is crucial, and ignoring these factors can lead to significant challenges. As we've explored today, the concept of time in distributed systems is far from simple. From the limitations of NTP synchronization to innovative solutions like Google's TrueTime API, understanding how clocks work and how they can fail can help us design more robust systems. The next time you think about time, remember, it's not just about the ticking clock. It's about the context in which that time is measured. Thanks for tuning in to Tech Talk. Until next time, keep questioning and keep learning.